Now let us see the three cases which comes under theory of damped vibrations. So now here we can see that in equation 20, when t varies, x also varies. So here the first case is b square is greater than omega square. That is the case of overdamping. So this is the nature of graph here. So when b square is greater than omega square, b square minus omega square will be positive. So in this case, we can see that root of b square minus omega square, when it is less than b, the exponential of equation 20 becomes decreased. So the displacement of x of the body gradually decreases exponentially with respect to time, and it comes to its equilibrium position at t it will be equals to infinity without performing any kind of oscillations. So this type of motion is called as overdamping or a periodic motion. So here this is the example here. Motion of pendulum in a highly viscous liquid. So when the pendulum is displaced from its equilibrium position, it comes to rest in overdamped movement. Here the overdamping is defined as it is the condition under which the restoring and resistive force action on a body are such that the body is brought to a halt at equilibrium position without any oscillation, but in a time greater than that which is the minimum time in which the same result could be achieved with the right combination of restoring and resistive forces. That is the case of overdamping. Next one is the case of critical damping. So in that case, b square will be equals to omega square. So when b square is equals to omega square, equation 20 cannot be analyzed. So its right side becomes infinity over there. To overcome the difficulty in it, root of b square minus omega square is assumed to be equals to very small quantity, that is E, and hence unequal to 0. That means in equation 14 you have to consider root of b square minus omega square is equals to E. Okay, so here you can write it as c into e to the power of minus b plus e bracket of t plus d into e to the power of minus b minus e bracket t. So we can write it as take e to the power of minus bt outside. Okay, then write. So now since e is very small, we can approximate here e to the power of et is equals to 1 plus et, and e to the power of minus et you have to take 1 minus et. Okay, now substitute this in equation 21. You will get this equation. Okay, now once again just rearrange it and write. Okay, so which is the product of two terms here. So when the t is present in e to the power of minus bt and also in the term c minus d e to the power of et, both of them contribute to the variation of x with respect to t. So now this critical damping is defined as it is the condition under which the restoring and resistive forces acting on a body are such that the body is brought to a halt at equilibrium position without any oscillation in minimum time. So that is known as critical damping. For example, Many electrical instruments like pointer galvanometer, voltmeter, etc. exhibit such kind of damping. So this pointer in the instrument, after receiving an impulse, smoothly comes to the displaced position without overshooting it or oscillating. So that is the second case. Next one is case 3, that is the case of underdamping. So here when b square is less than omega square, b square minus omega square is negative here. That means omega square minus b square will be positive. So therefore we can write root of b square minus omega square as root of minus of omega square minus b square. So here root of minus is nothing but I into root of omega square minus b square. So where I is equals to root of minus 1, and let us take omega square minus b square as n. So now equation 20 can be written as like this. So now write down x naught by 2, take e to the power of minus bt common from the both sides and write down. Now just simplify this and write. Then by Euler's theorem we know that e to the power of plus or minus I nt is equals to cos nt plus or minus I sin nt. Now substitute this in this equation. You will get x is equals to x naught by 2 e to the power of minus bt into 2 cos nt plus b by in into I 2 sin nt. Okay, now this I got cancelled and 2 is common on both sides, so it got cancelled. You will get this equation. Take it as equation number 22. Now let us take n is equals to alpha sin phi and b is equals to alpha cos phi. Take it as equation number 22. Now substitute the value of n and b in equation 22. So you will get this. So now you can write this equation as sin into nt plus phi, because this equation is related to sin a cos b plus cos a sin b. So that is nothing but sin a plus b. Okay, now write down x is equals to, so this part is taken as a. Okay, then a into e to the power of minus bt sin of nt plus phi. That is equation number 24. So here this is taken as a and phi is taken as tan inverse of n by b. Since the coefficient of the phase term always represents the amplitude in any equation for vibratory motion, that means this a into e to the power of minus bt in equation 24 is the amplitude of vibration of the body. As the time passes, this t increases, because of which e to the power of minus bt decreases. So this amplitude, that is a into e to the power of minus bt, therefore decreases progressively, resulting in damping of the vibrations. So this underdamping is defined as, it is the condition under which restoring and resistive forces acting on a body are such that the body vibrates with diminishing amplitude as the time progresses and ultimately comes to a halt at equilibrium position. So that is your third case for theory of damped vibration.